Hello students, welcome back. So in the previous session we have discussed regarding first 3 chapters of communication system subject. So in this particular session I am going to discuss the important points and formulas regarding remaining 4 chapters of communication system subject. Okay, right. So whoever missed the previous session, okay, so kindly watch that session in your free time. So for the timing you people can attend this session completely. Okay, so like as I mentioned earlier, so whatever the chapters, whatever we are going to discuss here, all the chapters will be there for EC branch, whereas for instrumentation only 2 chapters will be there. Okay, earlier we have covered 2 chapters, that is first chapter and second chapter, and here whatever remaining 4 chapters we are having. Okay, yeah, very good afternoon one and all. Yeah, so whatever the remaining chapters we are having, in that also 2 chapters will be there for instrumentation. So those 2 chapters are nothing but regarding digital communication. One is baseband data transmission, another one is band pass data transmission. Okay, so regarding those 2 chapters you can focus regarding whoever from instrumentation. I hope nowadays instrumentation students are also writing EC paper. So if you are writing for EC paper, then you can go through all the chapters of communication system subject. If you are focusing only with respect to instrumentation paper, then you can focus the first 2 chapters and then 5th and 6th chapter. Okay, total 4 chapters are there regarding communication system subject for gate exam point of view regarding instrumentation syllabus, whereas for EC branch all the 7 chapters are there for EC branch. Okay, so now we are going to start the next chapter, that is 4th chapter. So all of you put the heading chapter 4, random process and noise. Chapter 4, random process and noise. This chapter is only for EC branch. Okay, so I hope all of you might have studied regarding random variables in your mathematics subject, but once again here for understanding random process. Okay, so we will just discuss from the random variables so that you will get easily connected. Okay, if you already having very good command over the random variables, you can easily solve the questions related to this particular chapter. Okay, so the first one is probability distribution function, or other name of this one is cumulative distribution function. Probability distribution function or cumulative distribution function we used to represent with the letter capital F suffix capital X of x, fx of x, which is nothing but probability of x less than or equal to x. Probability of x less than or equal to x. Okay, so here the probability value, okay, whenever you are tossing a coin, okay, you will get, suppose either you may get head or you may get tail. Okay, so in order to get either head or tail, you are having the probability as 50%, or you can say 0.5. Okay, so whenever you are performing any random experiment, okay, so if you are getting whatever your desired outcomes, if you are getting the possible outcomes, whatever the among the possible outcomes, whatever your desired outcomes are there, if you are able to get, accordingly some probability will be there. If whatever your desired outcomes are there, if you are getting all those desired outcomes as the output, then we will say the probability of occurrence of that particular event is 1. Okay, so that means we can say the probability is varying from 0 to 1, right? The minimum probability is 0 and the maximum probability is 1, and here we are considering, or in other words we can say that whenever you are performing any random experiment, whatever the possible outcomes you are having, say for easy understanding you can consider that you are throwing a dice. Okay, so when you are throwing a dice you will get 6 possible outcomes, right? Either it may show 1 dot or 2 dots, 3 dots, etc. up to 6 dots. Okay, so for getting any possible outcome among those 6 outcomes, the probability is what? 1 by 6. When you are adding all the probabilities, then you are getting resultant sum equal to 1, right? So that means here cumulative probability, okay, we are adding all the probabilities, that means this particular function exists from 0 to 1, right? The function value exists from 0 to 1. So 0 less than or equal to fx of x less than or equal to 1. Okay, minimum value is 0 and maximum value is 1. Okay, so in other words we can write the same thing like this. fx of minus infinity is equal to 0 and fx of infinity is equal to 1. Fx of infinity is equal to 1. And here if you observe, the function is linearly increasing. Okay, linearly increasing function. Fx of x is a linearly increasing function, or we can say non-decreasing function, both are same. Fx of x is an increasing function. Okay, we can say it is an increasing function. It is an increasing function, or in other words you can say non-decreasing function, both are same. Either increasing function or non-decreasing function, both are same. Non-decreasing function. Okay, next property, this function is always, it is always continuous from right. Always continuous from right. Always continuous from right. So what is this meaning? You might have studied regarding the limits, okay, in your mathematics subject. When you are studying calculus, before starting differentiation, you might have studied regarding limits. Okay, so that time you might have studied regarding right side and left side, etc. Right. So that same concept only here we are going to use right. Okay, continuous from right. So here, okay, so here you can just make a note regarding that. If CDF is continuous everywhere, if CDF is continuous everywhere, okay, if the CDF is continuous everywhere, okay, that time fx of a minus fx of a plus fx of a all are same. That means you want to calculate the cumulative distribution function at one instant, okay, that is same as just slightly greater than a and that is slightly less than a. At all the three places you will get same. Okay, suppose if CDF is having discontinuity, if CDF is having discontinuity at x equal to a, suppose at x equal to a, if you are having discontinuity, that means just slightly before x equal to a you are having some value and slightly after x equal to a you are having other value. That means at x equal to a you are having discontinuity. Okay, so that time then in that case these two won't match. Okay, then that time fx of a minus fx of a plus both are not same. Fx of a minus fx of a plus both are not same. Just slightly before a, slightly after a, both are not same. But suppose in the exam if they asked that you have to calculate fx of x at x equal to a, that time what you have to do? As we have mentioned here, it is always continuous from right. So that means if you want to calculate fx of a, that one is nothing but fx of a plus. Okay, if you want to calculate at x equal to a, the probability distribution function, okay, that is same as just slightly after a, whatever the value you are having, that you can consider. Okay, next one, in some time, okay, suppose they may ask that probability at x equal to a, so that time you can consider like this, fx of a minus fx of a minus, or in other words you can consider a plus, here a minus, both are same. A plus and a both are same, that is the reason we have considered, and a minus. Okay, this is about probability distribution function. Next one is probability density function. this one we will represent with the small letters PDF. See, there also you are having similar probability distribution function. Here also probability density function. If you are considering the starting letters, same PDF only. That is the reason generally I will recommend that terminology cumulative distribution function, CDF, okay, so that you never get confusion whether it is distribution function or density function, okay. So regarding density function, fx of x is equal to differentiation of distribution function, okay, differentiation of distribution function. And from here you can do reverse, okay. Suppose if you are having distribution function, then you can perform differentiation, from there you will get density function. Similarly, if you are having density function, if you want to get distribution function, okay, so what you can do, you can just apply integration, that's all, just apply integration. Okay, if you want, you can consider limits from minus infinity to x, so that you are substituting the lower limit, but upper limit you are substituting x, so that means from there you will get in terms of x, okay. Next, coming to the probability density function properties. So here fx of x greater than or equal to 0, okay, because you are performing differentiation of distribution function. So since distribution function value exists from 0 to 1, obviously this particular function value you will get positive, okay. And one more important point, integral minus infinity to infinity, this is one of the most important relation in most of the questions, okay. In order to find some parameter, you can use this concept, okay. Integral minus infinity to infinity fx of x dx is equal to 1, okay. So regarding the probability density function, if they have given the expression in terms of, okay, one expression they have given, suppose in that they have given some unknown constant k. If you want to calculate that k with the help of this property, you can calculate. Here we are telling probability density function, we are performing the integration from minus infinity to infinity. That means from there you will get, in other words, like sum of all the probabilities equal to 1. And here we are using integration. Integration means, in other words, we can say integration is nothing but area under the curve. So area under PDF, okay, area under PDF. Area under PDF should be equal to 1. Area under PDF should be equal to 1. Okay, similarly, one more property, probability of x1 less than x less than or equal to x2. So if they are asking to calculate probability in this interval, then you can consider interval limits like x1 to x2, okay, then fx of x dx, fx of x dx. See, you can correlate like this. Here integral fx, okay, integral fx is nothing but capital Fx of x, okay. So that means fx of x2 minus fx of x1, right? So just like that you can correlate here, okay. When you are having 2 points like that in the interval, you can correlate, okay. Here I have considered like 1 point. Similarly, you can consider, okay, x lies between x1 and x2, then accordingly you will get capital Fx of x2 minus capital Fx of x1. Okay, this is about probability distribution function and probability density function. Now the next topic is expectation. Expectation operator. So regarding expectation of x, which is nothing but integral minus infinity to infinity x into fx of x dx, x into fx of x dx, okay. So here this one, if you want, you can label as m1. So that means you are getting the mean value of the random variable x. So if you are performing square of this one, that means m1 square, if you are calculating m1 square, that means expectation of x whole square. You are performing square of mean value, that means you are getting what? DC power, okay. For DC signal, whatever the mean value you are having, just perform square, from there you will get power. That power is nothing but DC power, okay, DC power. Next, second one, next expectation like m2 equal to expectation of x square. See, there is a difference between expectation of x whole square and expectation of x square, right? Here expectation of x whole square means first you are calculating expectation of x and then you are performing square. Whereas expectation of x square means you are in place of x you are having x square. So here in place of x you can substitute x square, that's all. So integral minus infinity to infinity x square into fx of x dx. Fx of x dx. So here you can observe you are performing expectation means mean. You are performing mean for square of the random variable, right? Mean, you are performing mean or average all are same. For what? Here for a random variable x, but here for a random variable which is having the square term, right? So accordingly we can call this one as mean square value. Mean square value. Mean square value. You are calculating the mean value for square of the random variable, right? So that's why we can call it as mean square value. Or in other words, in terms of power, since you are having square term, so accordingly you can call this one as total average power. Total average power. Total average power. Okay. So next one is variance. Variance equal to m2 minus m1 square. Variance equal to m2 minus m1 square. Okay. Now we'll discuss regarding the properties of expectation. Expectation of constant. Here k is the constant. So you'll get same thing. Expectation of constant is constant. Okay. Suppose if you are having expectation of constant times variable, that constant we can keep outside, multiply with expectation of x. Expectation of x. Next, expectation of ax plus b. Okay, here expectation operator is like linear operator. Why we are telling it is a linear operator, you can observe. Here, whatever the expectation operations we have done here, okay, in order to find, we are using what? Integration operation. So, integration operation, okay, suppose if you are having here addition of 2 terms or 3 terms, we can perform integration for each and every term. Yes or no? That's why we can apply the same concept here also. Expectation of some, whatever the expression they have given, in order to calculate the overall, you can perform, you can consider expectation is like linear operator. You can perform individually expectation, right? So from here what you will get? Expectation of ax plus expectation of b. So regarding expectation of ax, it is similar to this one. So you will get a into expectation of x plus expectation of, here b is constant, so that means you will get same constant b, right? Same constant b. Next, expectation of x plus y. You will get expectation of x plus expectation of y. Expectation of x plus expectation of y. Okay, so these are the properties related to expectation. Now let us see the properties related to variance. Variance of constant. Variance of constant. See here you can observe. Variance means what? m2 minus m1 square. m2 minus m1 square. But here that variable, instead of random variable, we have considered constant. Okay, so I already mentioned for constant expectation you are getting same. Okay, similarly, so that means here m1 square is nothing but k square. Similarly, m2 is nothing but expectation of x square, where x is nothing but k, right? So k square you are having, so k square you can keep outside. Integral minus infinity to infinity fx of x dx is nothing but 1. So that means you are getting k square. K square minus k square is nothing but 0. Okay, directly you can write variance of constant is equal to 0. Variance of constant is equal to 0. Okay. Next, variance of constant times x is nothing but k square into variance of x. K square into variance of x. Next, variance of ax plus b. Can anyone answer? Variance of ax plus b. See, just like earlier, you can perform variance operator just like linear operator, just like expectation. That time, here variance of ax, you will get a square variance of x, okay, plus variance of b, you will get 0. Okay, when you are adding 0 to anything, resultant answer will remain same. So that means final answer will be a square times variance of x. A square times variance of x. Okay, next one, variance of x plus y. Variance of x plus y, just like expectation of x plus y, you can write like this. You can write similar way. Okay, so that means variance of x plus variance of y. But there is a one condition. This relation will be okay provided if x and y are independent. Okay, if x and y are independent. If x and y are independent. If x and y are independent. Okay, suppose if x and y are dependent, that time we cannot make like this equation. Okay, so that time this is not equal. This is not equal. Okay, because there is some dependency is there, right? That is the reason. If x and y are independent, then only this relation holds good. Okay, otherwise it is not equal. If x and y are dependent. If x and y are dependent. Okay, so these are the properties related to variance. Okay, if you are able to remember these properties regarding expectation, regarding variance, you can easily solve the questions. Okay. Next one, the special random variables. So among that, first one is uniformly distributed random variable. Uniformly distributed random variable. Uniformly distributed random variable, right? So here as a name, uniformly distributed. So that means in one particular interval, or we can say on the x-axis, we are considering various x values, right? So in that, we are considering some range of x values for which this particular distribution function is like constant, or you can say uniform. Okay, so accordingly you can consider the probability density function like this. Fx of x is equal to 1 by b minus a for x lies between a and b. For x lies between a and b, 0 otherwise. See, you no need to by heart this one, it is very simple. Say for example, when you are considering a to b, that means on the x-axis, how much length you are having? B minus a. Okay, when you are considering uniformly distributed random variable, you will get one rectangular function. Okay, so rectangular function area is nothing but what? Length into height, right? So lengthwise you are getting b minus a, height-wise if you consider 1 by b minus a, then when you multiply both, you will get 1. Okay, earlier we have mentioned integration minus infinity to infinity, fx of x dx is equal to 1. That is nothing but area under the PDF. Both are same, right? So from there only you are getting that particular formula. Okay, simple logic. Whenever they are mentioning uniformly distributed random variable, okay, with respect to x-axis, how much length you are having, just take the reciprocal of that length as the height. Then when you multiply both, okay, from there you will get area under that particular curve will be equal to 1, right? So from there you will get like this, 1 by b minus c. Okay, and here if you observe, since the function exists from the interval in between a and b, okay, it is starting from a and up to b, and in this interval it is uniform. Uniform means it is a constant. Okay, so now in this particular interval, okay, with respect to which point the given graph is symmetrical, okay, either right hand side or left hand side, that particular point we will call it as mean or average, okay. So it is very simple. When you are having in the interval a and b, okay, if you want to find the average, just calculate average of these two, that's all, okay. So m1 equal to a plus b by 2, m1 equal to a plus b by 2. Next, m2 equal to a square plus ab plus b square divided by 3, a square plus ab plus b square divided by 3. Next, variance of x is equal to b minus a whole square by 12. Okay, all of you can easily remember regarding the first one, that is the average value. Okay, regarding this one, try to remember b minus a whole square by 12. Either if you want, you can represent b minus a or a minus b. But in general, when you are writing values a to b, that means b is greater when compared to a. But anyway, here you are performing square, definitely it will give positive value. Okay, b minus a whole square by 12. Just remember these two. After that, somehow, suppose if you are forgetting m2, in the question if they ask to calculate m2, you can derive. Even regarding this formula, if you are forgetting, no issue at all. Based on this formula, you can derive that m2. Okay, variance equal to m2 minus m1 square. Just bring m1 square on the side. From there, you can calculate m2. Okay, or otherwise, one more approach is expectation of x square. You can use this particular formula, and in place of fx of x, you can substitute 1 by b minus a, and then you can perform simple integration. From there also you can derive. Okay. If you are able to remember these formulas, then you can easily solve the question, because in the question they will give suppose 3 to 4 interval. Directly you can substitute a value 3, b value 4. From there directly you are getting the answer without using pen and paper. But suppose due to any reason if you forget the formula, no problem. Whatever the formulas here we are discussing, these formulas you can derive in less time. Okay, even during the GATE exam. Okay, so this is about uniformly distributed random variable. Okay, next one is exponential random variable. Next one is exponential random variable. So exponential random variable means the graph will be like exponential decay. For the timing we are considering like decay. Similarly, if you want, you can consider like increasing also. But for the timing we are considering exponential decay. So regarding that, the distribution function you will be having fx of x equal to alpha into e power minus alpha x. Alpha into e power minus alpha x for x greater than or equal to 0. Otherwise it is 0. 0 otherwise. 0 otherwise. Right. Next, here regarding the mean 1 by alpha, regarding m2 2 by alpha square. Okay, regarding variance 1 by alpha square. Regarding variance 1 by alpha square. Okay, regarding exponential, try to remember this. Okay, any two you can remember with the help of any two, other one you can derive. Okay, 1 by alpha square you can remember, and from there you can derive 2 by alpha square. So next one of the most important special random variable, that is Gaussian random variable. Gaussian random variable, the probability density function fx of x you will be having like this. Remember the standard equation, it is very important. 1 by root 2 pi into sigma square into e power minus x bar whole square divided by 2 sigma square. Divided by 2 sigma square. Okay, so here in this entire equation, if you observe, x bar is nothing but the mean, that is m1. Okay, and sigma x square is nothing but variance. Okay, So that means whatever this particular density function, when you have drawn on the graph, okay, you will get like bell shape. It is symmetrical with respect to the mean value. Suppose in some question they will specify that, or they will give another probability density function, but that is a derived version from here. Okay, suppose if x bar equal to 0, that means mean value is 0. See, if they have given like this equation, okay, in the question, in place of x bar they have mentioned 5, in place of sigma x square they have mentioned like suppose 49 example. Okay, then you can compare that equation with this equation. From there you can directly calculate mean and variance like that. Okay, suppose if x bar equal 0 and variance equal to 1, then you will get fx of x like this. You are getting the simplified version of this equation, right? Sigma x square is 1, so you are getting 1 by root 2 pi into e power minus, here x bar is 0, so that means you are getting x square divided by 2 sigma square. Sigma square anyway we have considered 1, so you are getting e power minus x square by 2, that's all. Okay, this is a simplified function. So when you are having the function like this, okay, in some question interestingly they never specify that this is the Gaussian random variable density function, but just suppose if they have given like this equation, okay, you can easily correlate. Okay, you can just compare like this. See, just observe regarding exponential you are having two. Okay, one is whatever earlier we have discussed, here exponential function. Okay, here also minus sign is there, here also minus sign is there, but the difference is when we are calling it as exponential you are having x power 1. Okay, but regarding Gaussian you are having x square. Okay, in that way also you can correlate. Whenever you are having x square term exponential, okay, x square term minus x square term, that time if you are unable to get how to solve that question, just correlate with respect to Gaussian random variable, try to compare the given equation with that, and from there you will get x bar, that is the first mean, m1, and then variance. After that you can calculate whatever the other parameter they are asking in the question. Okay, so up to here we have discussed regarding the random variables, that is distribution function and density function, and then we have discussed regarding the expectation values, first order moment, that is m1, m2 and variance. Okay, and then we have discussed the properties also. Now similarly we will discuss whatever up to here we have discussed regarding random variables. Okay, regarding these concepts I hope all of you studied in the mathematics subject also. Why I have discussed all these concepts? Because with this understanding you can easily correlate similar formulas you will be having when you are having two random variables, joint random variables. Okay, or even for understanding random process. Okay, next one, joint CDF. Joint cumulative distribution function. Joint cumulative distribution function. Yeah, here joint cumulative distribution function we will represent like this, fxy of x comma y. Earlier we have considered one variable, but now we have to consider two variables, right? So whatever the limits earlier you are having, same. It is starting from 0 and max value will be 1. It exists between 0 and 1. So earlier we have mentioned that fx of minus infinity equal 0. Okay, but here you are having two variables. If you are considering both the variables are minus infinity or any one variable as minus infinity, any one variable as minus infinity, you will get output as 0. Okay, suppose earlier we have considered fx of infinity equal to 1, so that means now similar one you will get if you are considering for both x and y infinity. Okay, then that time you will get 1. Next, so here you are having joint, that means two random variables, right? So if the given function like this, okay, suppose if you want to get only in terms of x or only in terms of y, okay, that time what you can do, if you want to get in terms of x, other variable you can keep infinity. Okay, so from there you will get, so fx of x equal to fxy of x you can keep as it is, y limit you can consider upper one, that is infinity. Okay. Similarly, if you want to get fy of y, so in fxy, in place of x, we have to consider the maximum limit, that is infinity. You are getting in terms of y. Okay. So these are nothing but marginal distribution functions. Marginal distribution functions. Marginal distribution functions, right? So this is about joint cumulative distribution function. With similarly, you will be having joint PDF, joint probability density function, joint probability density function. See, earlier we have mentioned fx of x is PDF we are able to get by performing differentiation, but here also we'll perform differentiation, but here you are having two random variables. Okay. So that means here we have to consider partial differentiation. Okay. So since two random variables you are having, you will get power 2. Okay. So fxy of x comma y is equal to dou square by dou square fxy of x comma y divided by dou x dou y, dou x dou y. Similarly, if you want to get fx of joint CDF, if you want to get from the joint PDF, you have to perform double integration. Okay, earlier since you are having only one variable, we have performed the integration with respect to one variable, right? But here two variables are there, so accordingly two integrals we have to consider. One integral with respect to x, one integral with respect to y. So the lower limit you can substitute minus infinity, upper limit you can substitute in one case x, another case y. Okay, so that you are getting function in terms of x and y. Okay, next, earlier we have mentioned that regarding probability density function, we have mentioned that value is greater than or equal to 0, because distribution function itself value is greater than or equal to 0, or it exists between 0 and 1. So obviously this particular density function you are having value starting from 0 and it is greater than 0. Okay. And similarly, earlier we have discussed one important property, area under the probability density function equal to 1. Similarly here, whatever here you are having, same thing you can consider, but upper limits you can consider infinity. Okay. Now this value will get equal to 1, Okay. So just like earlier we have calculated marginal distribution function, in a similar way marginal density function we can get from fxy of x comma y. Okay. If you want to get x, that time y limit you can substitute infinity. Similarly, if you want to get x, you can substitute y limit as infinity, like that. Okay. Suppose if you want to get fx of x, that means you have to perform integration with respect to y, because we have to eliminate, right? You can observe here you are having both x and y, but we want to get only x. If you want to get x, you have to perform integration with respect to y. Okay. Similarly, if you want to get y, that time you have to perform integration with respect to x. Okay, so these two are the marginal density functions. Marginal density functions. Okay, so earlier we have discussed expectation of x. Okay, similarly if they have given some function, right, for that function if they are asking expectation, in place of x you can consider entire function, right. So now say for example if they are asking that expectation of g of x comma y. So here you can perform, because you are having x, y, two variables are there, so accordingly you have to consider two integrals. Okay, integral minus infinity to infinity, this function you can consider g of x comma y into fxy of x comma y dx dy. Okay, how many variables you are having? That many integrals. Earlier we have discussed like expectation of x, integral minus infinity to infinity x into fx of x dx. Since only x is the random variable, that's why we have considered one integral. But here x, y are two random variables. Accordingly, we are considering two integrals. Okay, so now regarding the moments. Okay, so here with respect to x and with respect to y, here I am considering n and k. Okay, you can consider various n values, k values. Accordingly, you can calculate the moments, okay, or mean values. Various mean values you can calculate. M n comma k is nothing but expectation of x power n into y power k. Okay, now you can correlate. In place of g of x comma y, you are having this function. Now you can substitute this function. So accordingly, you will get. Okay. So here you will get double integral x power n y power k into fxy of x comma y dx dy. Now suppose here, see, while you are calculating this one, what is the order of the movement? That is nothing but n plus k. N plus k is the order of the movement. Like suppose if you want to calculate first order movement, okay, so what you can do, n value you can consider 1, k value you can keep 0. The moment you have put k value 0, y power 0 is what? 1. X power 1 is x. So expectation of x you are getting, that is m1. Okay, similarly you can consider n value 0, k value 1. That time you are getting expectation of y. That is also m1. Okay, so n plus k is given the order of the movement. Similarly, if you want to calculate m2, okay, so regarding m2, you will get, like suppose n value 2, k value 0. You can consider expectation of x square, or n value 0, k value 2, expectation of y square, or one more possibility is there, n value 1, k value is 1, expectation of xy, right? So then 1 plus 1 equal 2. So you are getting 3 cases like that. Okay, like that, whatever they are asking in the question, accordingly you can calculate. Okay. So next one is autocorrelation function. This is one of the most important autocorrelation function. Autocorrelation function, that means we are performing the correlation operation with respect to the same function, right? So Rxx of tau you can represent, or in short you can represent as Rx of tau, because you are representing or you are correlating with the same random process x of t, right? So Rxx of tau is same as Rx of tau, which is equal to expectation of x of t into x of t plus tau. X of t into x of t plus tau. So that means you are considering one random process at one instant t, another same random process you are considering, but one more instant like t plus tau. Similarly, if you want, you can consider t minus tau also. If you want, you can consider t minus tau also. It will be satisfying. So that means what is your observation? Here you are having the autocorrelation function. It is not a function of time. Rather, it is a function of difference of those two time instants. Yes or no? Difference of those two time instants. Difference of these two, tau. Difference of these two, you will get tau, right? See, when you are having these two time instants, obviously this is greater when compared to this one. Difference you will get tau only, right? That is the reason. Here autocorrelation function, it is depending, or you are getting function function of time difference, not rather on absolute time. That is the reason, or you can correlate here. When you look at these two equations, here plus tau is there, here minus tau is there. That means in place of tau, when you are considering minus tau, if you are getting same function, that means that given function is satisfying which symmetry? Any guess? I hope all of you are familiar. In place of tau, if you are keeping minus tau, you are getting Rx of minus tau, right? So Rx of tau, Rx of minus tau, both are same. So that means it is satisfying which symmetry? It is satisfying even or odd? All of you can answer. Rx of minus tau is equal to Rx of tau. It is even symmetry, right? Even symmetry. Okay, if it is odd symmetry, you will get minus. Next, consider tau value 0. Consider tau value 0, either in the first equation or second equation, no problem. So here x of t, here also x of t. X of t into x of t, you will get x square, right? So you are getting Rx of 0. Rx of 0 is nothing but expectation of x square of t. Expectation of x square of t. Okay, and one more important relation. See here the beauty of this question. Okay, this property especially. See earlier when you are having expectation of x square, we have discussed that integral minus infinity infinity x square into fx of x dx. Okay, that formula you can use provided when they are giving with respect to that random process the corresponding density function. But in some question, surprisingly they won't give the density function, but they will ask that expectation of x square of something, expectation of x square of 5 or expectation of x square of 3, like that. But in that question they will give the autocorrelation function expression. Okay, so that time what you have to do, since they have given autocorrelation function, just recall the standard definition of autocorrelation function, right? The moment you have written the expression, how you are able to get expectation of x square of t, just you can figure out. In place of tau, if you are putting 0, x of t multiplication, that means x square of t. That means whatever the autocorrelation function they have given, in that function just consider tau value 0. From there you are directly getting this particular value. And one more interesting thing. So whether they are asking expectation of x square of 3 or whether they are asking expectation of x square of 5, whatever may be the time instant, they may ask regarding expectation of x square value, all will give the same answer. Okay, no need to calculate for everyone. Okay, every time no need to calculate. The moment you have calculated for expectation of x square of 3, the same answer will be there. Expectation of x square of 5, expectation of x square of 7, whatever may be the time instant. Why? The reason is very simple, because expectation of x square of t, that value you are not getting by substituting t value. Rather you are substituting, the moment you are substituting tau value 0, from there you are going to get. Okay, so here in the autocorrelation function, the moment you are substituting tau equal 0, from there whatever the expression you are going to get, the same answer will be applicable whatever the time instant you are considering, right? So this is one of the most important formula or relation. Okay, if you are able to remember this formula, you can easily answer such kind of questions. Okay, right. And one more important relation regarding autocorrelation function. So Rx of tau, magnitude wise I am considering this value is always less than or equal to Rx of 0. So that means autocorrelation function at tau equal to 0, you are getting maximum value. Okay, and remaining in the interval, okay, what is the time axis you are having? So in that interval regarding autocorrelation function, when compared to this one, you may get equal or you may get less, but maximum value you are going to get at tau equal to 0. So this is about autocorrelation function. Similarly, if you are considering one random process x of t, another random process y of t, then if you want to find the correlation, then accordingly the name is cross correlation. Okay, whenever cross correlation is there, that time definitely they will represent x, y. But whenever autocorrelation function is there, that means sometimes they will represent like this or sometimes they can represent like this, because it is self-understandable, because we are just perform the correlation with respect to same random process, right? Next one, cross correlation. Cross correlation. Cross correlation means Rxy of tau. Cross correlation means Rxy of tau. So Rxy of tau, you can write it as expectation of x of t into y of t plus tau. Similarly, if you want, you can consider y of t minus tau, no problem. Okay, later you can write. So you can write the conclusion points regarding if based on the autocorrelation function. Suppose if you are getting cross correlation function as 0, if Rxy of tau equal to 0, okay, that indicates x of t and y of t are orthogonal. If Rxy of tau equal to 0, okay, that implies x of t and y of t are orthogonal. X of t and y of t are orthogonal. X of t and y of t are orthogonal. Okay. Next point, if x of t and y of t are independent, if x of t and y of t are independent, if x of t and y of t are independent, then cross correlation function Rxy of tau is this function. The moment x of t, y of t are independent, you can perform independently expectation operation. Then expectation of y of t plus tau is same as expectation of y of t. So from there directly I am writing expectation of x of t into expectation of y of t. Okay, the moment if x of t are y of t are independent, cross correlation is nothing but expectation of x of t and expectation of y of t. Okay, if cross correlation function is equal to 0, that means x of t and y of t are orthogonal. Okay, these relations are important. In some question they will specify the conditions, they will ask the corresponding, or in some question they will give some relation regarding cross correlation, and from there they will ask the relation, etc. Okay. So next one is autocovariance. Okay, earlier we have discussed variance, right? Similarly here covariance, we are using the term covariance. So covariance you will be having auto and cross. Okay, so first one is autocovariance. Autocovariance. So here we will represent Cxx of tau. So variance is nothing but what? M2 minus M1 square. M2 minus M1 square. So M2 value just now we got. You can observe M2 value just now we got. This is nothing but M2. Okay, if you want, you can write this one as M2. Yes or no? M2 is nothing but this one. Okay. Okay. So here M2 is nothing but Rx of tau. Okay, you can correlate like this, expectation of x of t into x of t plus tau, that is nothing but autocorrelation function. Okay, that is M2. And coming to M1, expectation of x of t and then square. Okay. Yeah. So here you can write autocorrelation function Rx of tau minus expectation of x of t whole square. Expectation of x of t whole square. If they are mentioning in place of tau some value, then accordingly you can substitute. Okay. But just for correlation I have mentioned this is M2 and that is M1. Okay, M2 minus M1 square. Next one, cross covariance. Cross covariance, that means Cxy of tau, Cxy of tau. Okay, just by observing the previous equation you can write this one. Here autocorrelation, but here cross correlation. Okay, Rxy of tau. Here expectation of x of t into expectation of x of t you can write. Here x is there and y is there, right? So similarly you will get expectation of x of t into expectation of y of t. Expectation of x of t into expectation of y of t. Okay. Suppose you can make a note, if x of t and y of t are independent, if x of t and y of t are independent, see regarding this we already seen, just you can observe, if x of t and y of t are independent, cross correlation is same as the product of individual expectation, right? So you can observe, whatever the second term you are having, the first term both are same magnitude wise, but here minus sign is there, overall term you will get 0. Okay. If x of t and y of t are independent, then cxy of tau is equal to 0. Cxy of tau is equal to 0. If x of t and y of t are independent, then cxy of tau equal 0. So next point you can make a note, if cxy of tau is equal to 0, that means here cross covariance, right? Among x and y we are observing variance. Okay, if you are getting 0, okay, with respect to independent you are getting that relation, but whenever cxy of tau equal 0, that means there is no relation between x of t and y of t, right? So in other words we can say that those two are uncorrelated. Okay. So if cxy of tau equal 0, then x of t and y of t are uncorrelated. X of t and y of t are uncorrelated. Okay, so up to here whatever we have discussed regarding autocorrelation and cross correlation and then corresponding variance, autocovariance and then cross covariance. Okay, these conclusion points are very important while you are solving the questions regarding this particular chapter. Okay, next one we are having regarding autocorrelation function and the corresponding Fourier transform is power spectral density. Okay, so autocorrelation function Rx of tau, if you apply Fourier transform you will get power spectral density Sx of f, that is the power spectral density. So here power spectral density units will be watt per H. So obviously the power spectral density will be greater than or equal to 0. Power spectral density always greater than or equal to 0. Okay, and one more important property, in some question they will ask that the power of that particular signal, right? So if you perform the integration of power spectral density, from there you are getting the power. Integration of power spectral density with respect to frequency. Okay, from there you are getting the power. See, you can observe here power spectral density units are what? Watt per H. You are performing the integration with respect to what? Frequency. That means you are multiplying this one with H, then H will get cancelled. From there you are getting power. The units are watt, that's why we have mentioned average power, right? Next, one more important property regarding the power spectral density. Just like autocorrelation function is an even function, in a similar way the corresponding power spectral density, it is also even function. Sx of minus f is same as Sx of f. Okay. Next, one more point, this is also most important. The power spectral density is always real. Okay, there won't be any complex term or imaginary term. Okay. So here whatever the properties you are studying regarding power spectral density, in sometimes they will give regarding the power spectral density graph. Okay, they will ask that you have to identify the valid power spectral density. Okay, so that time with the help of these properties you can easily answer. Okay, so with respect to even symmetry you can cross check, with respect to this property you can cross check. Okay, with respect to this property also you can cross check, like that. Okay, but sometime they will give power spectral density graph, they will ask the average power, right? So that time you can use this property, right? And sometime they will give autocorrelation function, they will ask power spectral density, or they will give power spectral density, they can ask autocorrelation function, right? So for that you have to apply inverse Fourier transform. Okay, whatever the knowledge you have learned from the signals and system subject regarding Fourier transform, so that knowledge will be helpful while you are solving the questions of communication system subject also, right? And one more important relation, so here regarding output power spectral density, output power spectral density equal to input power spectral density, into magnitude of transfer function whole square. This is one of the most important relation. Okay, so they will give one LTI system, they will give the input power spectral density, but here if they are asking input power spectral density power, then you can use this one. But surprisingly they will ask output, regarding output of that particular filter they will ask the power. That time you have to calculate output power spectral density first, after that you can perform the integration with respect to frequency, from there you can get the output power. Okay, so how to remember this equation, I will give the one easy hint point. Okay, see, generally when you have studied regarding control system subject, while you are studying block diagram representation, right? So when you are having one block, okay, suppose you are having transfer function is like h of s. If the input is x of s, output you are writing y of s equal to x of s into h of s. Like that, here this is the transfer function only. When you are representing in s domain, you are writing h of s. When you are representing Fourier transform or normal frequency, h of f or h of omega, like that, right? So similar formula, but only the difference here you are taking magnitude of the transfer function and then square. Okay, in that way you can correlate, so that you will get output power spectral density by multiplying input power spectral density and magnitude of transfer function whole square. Okay, right. This is one of the very, very important relation. One of the very, very important relation. Yeah. Next one, regarding figure of merit. Actually this concept belongs to the previous chapter only, but generally I used to cover this concept in this chapter because whatever the random process concept, okay, that we have studied, with the help of that we can do the noise analysis part. Okay, but since it is a revision class, I am not discussing any formula regarding derivation part, just I am giving the direct formulas. Okay, so figure of merit we used to calculate for the receivers, whatever the receivers we have studied. Okay, with the help of whatever the modulation techniques we have studied with the help of first chapter and second chapter. So for all those modulation techniques, okay, we will analyze with the help of figure of merit which receiver is the best. Okay, or which receiver we can use among the available receivers, with the help of which modulation technique. Okay, if you are passing or if you are transmitting the signal at the receiver, when you perform the demodulation, from the demodulation whether you are able to get the message signal properly or not. If you are able to get even in the presence of noise, that means that that receiver we can say it is a better. Okay, if you are able to get among all the other receivers, with the help of one receiver, if you are able to get in the better manner, that means we can say that is the best receiver, right? So figure of merit is nothing but signal to noise ratio at the output of receiver, divided by signal to noise ratio at the input of receiver, Okay, right. So regarding DSBSC, regarding SSBSC, and similarly for VSBSC, for all these three receivers, the figure of merit value is same, that is 1. Figure of merit equal to 1. Okay, output SNR, input SNR, both are equal. Okay, so based on that you are getting the ratio as 1. Okay, So whereas the figure of merit for AM, that is the first modulation technique. So for that you are getting mu square by 2 plus mu square. Whatever the modulation efficiency formula we have discussed, same formula, mu square by 2 plus mu square. Okay. So regarding AM, when we have discussed, okay, so the mu value generally we will consider maximum value, there it is 1, right? Suppose if you have considered modulation index value as 1, if modulation index is 1, that time we are going to get figure of merit for AM, how much? So 1 divided by 2 plus 1, that is 1 by 3. So 1 by 3 is what? Less than 1. 1 by 3 is less than 1. So here among DSBSc, SSBSc, VSBSc and AM, all these three are getting 1, but whereas here we are getting less than 1. So that means when you compare with any of these three, okay, AM is not at all recommended. Okay. Now coming to the figure of merit for FM. Figure of merit for FM. So regarding this, you can remember the formula. You will get 3 by 2 times beta square. 3 by 2 times beta square. Yes, Akanksha. Yeah, regarding that I will discuss in the last chapter. Okay, in the last chapter I will discuss. Okay, so here figure of merit for FM, that is 3 by 2 times beta square, right? So here this figure of merit we are discussing for what? Wideband FM, wideband FM. Because for narrowband FM and AM similarity you are having, right? So obviously here beta value is what? Greater than 1. The moment you have considered beta value greater than 1, beta square will be even greater than 1, and that one you are multiplying with 3 by 2. So from there you are getting figure of merit value. Obviously here you are getting 1, but here figure of merit you are getting far greater than 1, right? So that means among all the receivers, FM is the best. Among all the receivers, FM is the best. FM is the best receiver, because here we are using frequency modulation concept. The moment you are using frequency modulation concept, whatever the noise spot is there, we can easily eliminate that noise spot. Okay, that is the reason here among all the receivers, now I am given the conclusion point, FM is the best. Among analog modulation techniques, which one is the best means SSBSc among all, with respect to bandwidth, with respect to power, okay, with respect to quadrature null effect, among all, if you consider SSBSc is the best among analog. Okay, among analog. And so if you want to compare analog modulation, sorry, amplitude modulation and then angle modulation together, if you are considering overall analog communication, if you consider, so in that FM is the best, like that. Okay, so up to here we have completed 4 chapters, right? So the next chapter, so up to here whatever we have discussed, it is like mostly analog part. Okay, of course in this chapter we have discussed regarding random process, random variables, etc. and noise part also. Okay, so the next chapter, so whatever now we are going to discuss, that is regarding digital communication. Okay, so all of you put the heading chapter 5. Chapter 5. Chapter 5, digital communication. So regarding digital communication, we are having 2 chapters. Okay, the first one is baseband data transmission. Baseband data transmission, right? So this chapter and next chapter is common for both the branches, EC and instrumentation. For both the branches, okay, for both the branches EC and IN, we are having digital communication 2 chapters. Both the chapters are part of the syllabus. Okay, so in this digital communication, okay, so regarding baseband signal, we already mentioned earlier, baseband signal means the signal exists in the low frequency range, okay, or we can say the signal exists around 0 frequency when you draw the spectrum, okay. Coming to the next one, in the next chapter we will use band pass radio transmission. Band pass means we are representing that signal, or we are transmitting the signal which is having the spectrum centered around some high frequency, that's all, okay. That is the only difference, okay, between baseband and band pass. Baseband means low frequency signal, band pass means high frequency signal, or centered around some high frequency, we can say, okay. So here the first modulation technique is pulse code modulation. So in the pulse code modulation, we are having whatever the analog signal we are having, we have to convert into digital, okay. So in the signals and system subject, whatever the operations you might have studied, okay, or whatever the types of signals you have studied, so those signals you will be coming across while you are converting analog signal into digital in this communication system block diagram, okay. Especially in the PCM concept, pulse code modulation, first we will use sampler. With the help of sampler circuit, you are taking the sample signals. After that we are doing the quantization, and then with the help of quantization, whatever the amplitudes you are having, various levels, we are making into finite levels. After that, those finite levels we are representing with the corresponding number of bits, okay. So with the help of encoder, we are getting the corresponding digital signal, okay. So mainly you are having three blocks, one is sampler, another one is quantizer, and another one is encoder, okay. So what are the important relations or formulas are there that are regarding PCM, I am going to cover now. So while you are doing the sampling, okay, so I hope all of you know that the sampling frequency should be greater than or equal to 2 times FM. Here 2 times FM is nothing but the Nyquist frequency. Then only at the receiver, when you want to get from the sample signal your actual signal, you can extract your signal, otherwise you will lose the information, okay. So next one, step size. Step size we used to represent with the symbol delta, so that is equal to dynamic range divided by number of quantization levels. Number of quantization levels. Okay. Next, regarding quantization error is nothing but current sample, that means sampled value minus quantized value. Sampled value minus quantized value. Sampled value minus quantized value. Okay. So regarding QE max, quantization error max, you will get half of the step size, because we are using mid-rise quantizer, right? So in general the QE will vary between, QE varies from minus delta by 2 to plus delta by 2. QE varies from minus delta by 2 to plus delta by 2. So that's why when you observe among all these quantization errors, you are getting the maximum value plus delta by 2. That's why I have represented here plus delta by 2. Quantization error maximum is half of the step size. Okay. And regarding the number of levels, so I hope all of you know the relation between the number of bits and number of levels. If you are having 2 bits, you are getting 4 levels. If you are having 3 bits, you can get 8 levels, like that. Next, the bit duration TB equal to the sampling time divided by number of bits. So just take the reciprocal, from there you will get bit rate. RB equal to 1 by TB. Now just reciprocal this one, you will get N by TS. 1 by TS we can write as sampling frequency. Now you can observe regarding N, which are nothing but number of bits we are using for sample. Right? So regarding sampling frequency, So since you are mentioning frequency, you can mention units or hertz. Okay, but here we are going to get in terms of bit rate. So accordingly, frequency is nothing but you are getting hertz, so that is nothing but reciprocal of time. So that means per second, right? So here, in other words, you can represent samples per second. Sampling frequency, how many samples you are having in per second. Okay, so here sample will get cancelled, you are getting bits per second. So here we are having that bit rate, that means in 1 second how many bits we are transmitting, right? So the units will be bits per second. So in short, we will represent BPS, bits per second. So from here, whatever the bit rate you got, that will be your bandwidth. That will be bandwidth. Okay. So here, if you observe this entire formulas and all, okay, the main important thing is whatever the information you are getting after doing all these steps like sampling, quantization and encoding, if you want to get accurate results, okay, so that means the error should be as minimum as possible, especially the quantization error should be as minimum as possible. If you want to make the quantization error as minimum as possible, you have to increase. You can observe here. So quantization error, you are getting half of the step size. So regarding step size, you are having the formula this one, dynamic range divided by number of quantization levels. Here dynamic range anyway we cannot change that, suppose for that particular signal it is fixed. Now the only possibility with respect to quantization levels, and regarding this the relation is this one, L equal to power n. So the moment you are increasing number of levels or you are increasing number of bits, so based on that the step size is going to reduce. Once step size is reduced, quantization error is going to reduce, right? That is the advantage. But coming to the bandwidth or bit rate, because here n value if you are increasing, according the bit rate is increasing and bandwidth also increasing. That is a drawback of pulse code modulation. Otherwise, pulse code modulation is like one of the best modulation, or we can say it is a easy method. Okay, but only with the help of that, because in order to reduce the quantization error, obviously you have to increase number of bits. The moment you are increasing number of bits here, automatically the bit rate also getting increased. Okay, that is the only drawback with respect to PCM. Now next one, here whatever the error you are getting, that is because of quantization process. So accordingly, in general we used to call because of noise. Okay, if you want to analyze whether that particular modulation technique or any technique whether we can use or not, in order to verify, we will use the parameter like signal to noise ratio. In the similar way, here also we are using signal to noise ratio, but that noise is coming because of quantization, right? So accordingly here, okay, after doing the simplification and all, you will get the standard formula. So directly you can note down signal to quantization noise ratio. Signal to quantization noise ratio, the formula you will get 3/2 times 2 power 2n. 3/2 times 2 power 2n. So this formula you can use whenever they are giving normal value, but some question they will give this value in terms of decibel. Okay, so signal to quantization noise ratio in decibels. Whenever they are giving in the order of decibels, okay, that time you can use this formula 1.8 plus 6n. 1.8 plus 6n. So that moment you are increasing the number of bits, accordingly the signal to quantization noise ratio is increasing. So that means it is the best only. Whatever earlier we have told with respect to normal formula, the same conclusion point you are going to get. Okay, so this also, what are the formulas we have discussed regarding PCM, all the formulas are very important. You will get direct questions based on these formulas. Okay. Yeah, next concept, as I mentioned earlier, in the first chapter we have discussed regarding multiplexing in the frequency domain, that is FDM, frequency division multiplexing. That time I have mentioned that we are going to use time division multiplexing in the 5th chapter, right? So now in the pulse code modulation, whatever in the pulse code modulation, what you are doing, you are having one signal, analog signal. For that signal, you are doing the sampling, quantization, encoding. Like that, if you want to transmit multiple signals in the same channel, okay, that time you can use multiplexing concept. But now here we are using on time basis. On time basis, we are taking the sample from one signal. Okay, for every TS interval, we are taking one sample from a particular signal. Okay, now that time they will ask what is the bit rate, etc. Okay, so for that you you can remember these formulas regarding time division multiplexing. Okay. So here regarding bit duration, TB equal to, so earlier you are having like TS by N, okay, but here similar formula you will get, but in the denominator there will be slight modification, N into N plus A, just take the reciprocal, from there you will get RB, that is bit rate, so NN plus A into 1 by TS is nothing but Fs, okay. So here Fs is nothing but sampling frequency, that you know, and N is the number of bits per sample, that also you know, and here capital N is what? Number of signals that you are transmitting. Capital N is the number of signals that you are transmitting, whether 2 signals you are transmitting or 3 signals, 4 signals, like that, okay. So here regarding small a is what? In general, when you are transmitting number of bits, okay, there will be synchronism, okay, with respect to input and output, or we can say in the channel, okay, in order to provide, okay, which one is the ending bit or which one is the starting bit, etc. So just in order to know, we will add some synchronization bits. So here A is nothing but number of synchronization bits. A is nothing but number of synchronization bits. Suppose in some question they won't specify regarding number of synchronization bits, that time you can consider like 0. Suppose if you are having number of signal only 1, right, that time you are getting N into Fs, whatever the formula earlier you have got, same formula, okay. This formula is like without using multiplexing, or multiplexing special case, when you are considering only one signal, this formula will come like that, okay. So generalized case, this formula, and from here you can get back your earlier formulas, okay. So regarding PCM, we have told the drawback. The drawback is what? As you are increasing N, the bit rate is increasing, accordingly bandwidth also increases. That is the drawback. Now to overcome this drawback, okay, now we will use another technique, that is called DPCM. Next one is DPCM, differential pulse code modulation. So in this technique we are using pulse code modulation only, but only the difference in the pulse code modulation, directly what is the analog signal you are having, for that signal we have considered the sample, okay. But now in the DPCM we are going to give input as difference of 2 samples, okay, the present sample and previous sample. So you can write down in DPCM system, input to quantizer is equal to present sample minus previous. Present sample minus previous sample. Present sample minus previous sample. So with the help of this one, we are like here what we are doing is, at least dynamic range wise we are just making somewhat less, okay, that is the reason, okay. So here if you want you can make a note, it is used to, this DPCM we are using, it is used to reduce the quantization error without increasing the number of bits. Reducing the quantization error without increasing the number of bits, okay. But whatever the formulas earlier we have discussed regarding bit rate, all other formulas regarding PCM, all those formulas will be equally applicable with respect to here, okay. Now so next one from DPCM, one special case, okay. Just like here we are performing the difference, but after that whatever the value you are getting, that value we are giving as input. But here if you are getting the difference is positive, then we will consider one step size positive, okay. If you are getting negative value, we will decrease the one step size, like that. Accordingly we are getting the next modulation, that is delta modulation. Next one is delta modulation. So in this case, if present sample minus previous sample, present sample minus previous sample is positive, then we are increasing one step size. We are increasing one step size. Okay, suppose if you are getting present sample minus previous sample, present sample minus previous sample, if you are getting negative, that time we are decreasing one step size. We are decreasing one step size. Okay. So the advantage of this delta modulator is either you are increasing one step or you are decreasing one step. Okay. So for increasing one step or for decreasing one step, one bit is sufficient. That means we can say that whatever the delta modulation is there, that is nothing but one special case of your DPCM, that's all. Or in other words, we can say that it is 1 bit DPCM. So delta modulation is nothing but 1 bit DPCM. 1 bit DPCM. Okay. So whatever the formulas earlier we have discussed, same formula you can use. RB equal to N into Fs, but here N value is 1, so 1 into Fs. 1 into Fs. Okay. So that is nothing but sampling frequency Fs. Now take the reciprocal. So RB is nothing but 1 by Tb and Fs is nothing but 1 by Ts. So from here you are getting Tb and Ts both are same. Tb and Ts both are same. Bit duration and sampling time both are same. So regarding delta modulator, okay. So you are having original signal is m of t. Original signal is m of t. So perform the differentiation. That means you are getting slope of the actual signal, right? Slope of the actual signal. So if you want, you can consider like modulus, right? This is the slope of actual signal. Slope of actual signal. But after performing demodulation, so here you will get, okay, the height wise either plus delta or minus delta, like that you will get, okay. And for every sample, horizontal you are having sampling time interval, okay, one sample to other sample you are having Ts duration, right? So that means here output of demodulated signal, or slope of demodulated signal, slope of demodulated signal, so here you will get delta by Ts. Okay, here also I am considering modulus, so that see the difference you may get positive or negative, but Ts value always you will be having positive. Okay, so that's why just for easy understanding we are considering always modulus. Okay, so here actual signal slope and demodulated signal slope, if you are getting both are same, that means there is no error. Okay, suppose if this is greater, you will get one error. If this is greater, you are getting other error. So that means here the most important thing in the delta modulation, you have to choose the delta value in the better manner. Okay, if you are able to choose delta value in the best manner, then definitely you will get, there won't be any error. Okay, there won't be any error at all. But so if you are not choosing the delta value appropriately, then accordingly you may get error. That is the only drawback. Okay, of course if some error is coming, then accordingly you can overcome. Okay, right, there is no issue. So suppose here if delta by Ts is less than dm of t by dt, so that means here step size is less when compared to the slope of the actual signal. That means you are getting slope overload distortion. Then you are getting slope overload distortion. Or you can say slope overload error, all are same. Slope overload distortion or slope overload error. Okay, so whenever this occurs, that time you have to increase step size. If you are increasing step size, then this problem we can work. Okay, next another case, if delta by Ts is greater when compared to this slope dm of t by dt, that time you are going to get another noise that is called granular noise. Granular noise. Okay, so regarding this particular chapter, we are having one more important topic, that is matched filter receiver. Matched filter receiver. Matched filter receiver. So regarding the matched filter receiver, one of the important relation regarding signal to noise ratio maximum, that is 2 times E by N naught. 2 times E by N naught, where E is the energy of the signal, and this numerator 2 if you bring to the denominator, from here you will get like E by N naught by 2, where N naught by 2 is nothing but the power spectral density of white noise for double sided. Okay, so this relation you got in order to get the derivation. See, in general you might be having the various filters like low pass filter, high pass filter, band pass, band stop, like that. Okay, any other filter accordingly the name, okay, you are having the corresponding transfer function, but here we are using the filter name as matched filter. Okay, so this very interesting word, the word matched filter. So regarding this one, you, in order to find the impulse response, while you are deriving, in that proof you are getting one of the relation we have to use, from that you are getting like this relation. Okay, and regarding this matched filter, it is very simple. Regarding the matched filter impulse response, h of t equal to whatever the input signal you are applying. Regarding the input signal, you have to consider the conjugate of that. Okay, conjugate of that. So TB minus T. Okay, initial signal you are having S of t. For that signal you have to perform conjugate of TB minus T. Okay, suppose if S of t is real, then the impulse response will be h of t equal to, complex conjugate is same as normal only, because S of t is real, there is no imaginary term at all. So h of t equal to S of TB minus T. Okay, suppose S of t if you are considering one pulse. Okay, so that pulse when you perform the reversal, time reversal, and when you perform the shifting operation, after that whatever the signal you are getting, that signal is exactly same as your original signal. Okay, that is the reason here we are calling it as matched filter. Okay, right, h of t equal to S of TB minus T. Okay, in some question they will ask only the matched filter impulse response. In some question they will ask what is the output of matched filter. Okay, what you have to do in that case, first of all you have to calculate h of t. After that, the way you have learned for any LTI system, okay, if you are having x of t is input and h of t is impulse response, in order to find the output, you might have solved that kind of questions in your signals and system subject by using convolution operation, right? Same logic you can apply here also. Okay, if they are asking output of matched filter, if they are asking output of matched filter, so y of t equal to here h of t, you got h of t convolved with s of t, or s of t convolved with h of t. In any order you can write, there is no issue at all. S of t convolved with h of t or h of t convolved with s of t. Any order you can write, no problem. So I hope all of you know, suppose if you are having both the rectangular functions, okay, if you are performing the convolution, then you will get triangular function. Okay, if both the rectangular functions are having the same duration, then you will get triangular function. Okay, if both the rectangular functions are having non-equal duration, okay, that means different duration you are having, then that time you will get trapezoidal signal. Okay, and here one more important note. Okay, in some question they will ask like this, regarding the matched filter output, the peak value they will ask. Okay, so you can make a note, peak amplitude of matched filter output. Peak amplitude of matched filter output is equal to here whatever the input signal you are having, regarding that just calculate the energy. So both will be same. Energy of the matched filter input. Energy of the matched filter input. Okay, that time it is very simple. Whatever the input signal you are having, regarding that particular input signal, just calculate the energy. Okay, energy is nothing but what? Integral P dt. If you want, you can calculate power and then you can perform the integration of that power. From there you will get energy. Okay, so that energy will be same as the peak amplitude of the matched filter output. Yeah, up to here we have completed regarding 5th chapter, right? So now let us move on to the next chapter, that is 6th chapter. This is also digital communication. Chapter 6, digital communication. But here band pass. Okay, earlier it is baseband, but now it is band pass. Band pass data transmission. Band pass data transmission. Digital communication, band pass data transmission. So just like in the first chapter and second chapter we have discussed like amplitude modulation, frequency modulation, phase modulation. In a similar way here also you will be having amplitude shift keying, frequency shift keying and phase shift keying. Okay. So first one is here, okay, instead of making like separate, okay, I will make like tabular form so that you can easily correlate. Okay, here I will mention IISc, then next one is PSK and next one is FSK. 3 modulations we are having: amplitude shift keying, phase shift keying and frequency shift keying. So first of all, regarding modulator, name of the modulator. So here we will use product modulator. Product modulator. Here in PSK also same, product modulator only, same. Whereas in FSK we will use voltage controlled oscillator. We will use voltage controlled oscillator, just like in the FM we are using the direct method. Okay, similarly here with the help of voltage controlled oscillator you will get the frequency variation in accordance with the message signal. Okay. Next, here coming to the signaling, coming to the input signaling, I mean to say regarding the binary signaling. Okay, regarding binary, what kind of signaling we have used? In the ASK we have used on-off signaling, whereas in PSK and FSK we have used non-return to zero signaling. Non-return to zero signaling. Okay, here non-return to zero signaling means if you are having bit value 1, that means we used to represent positive voltage, bit value 0 means negative voltage. Similarly there. Whereas on off signaling means bit value 1 means 5 volt, bit value 0 means 0 volt, like that. Okay. Next, here we will get the time domain equations. Okay, next one, time domain equations. So here in one interval you will get the output as, when you are considering on, that means bit value 1, so that time you will get S1 of t equal to AC into cos 2 pi of Ct, right. So another bit interval you are getting 0, another bit interval you are getting 0. Okay, whereas for PSK signal, S1 of t, you will get AC cos 2 pi of Ct when you have considered positive voltage here, AC cos 2 pi of Ct. Okay, another interval you are getting, because of minus sign, you will get minus AC cos 2 pi of Ct. This minus sign, if you want to represent, you can write it as AC into cos 2 pi of Ct plus 180, like that also you can represent. Okay, coming to the frequency shift keying. So here, for bit value 1, you are getting the maximum frequency. For bit value 0, you are getting minimum frequency, right? So accordingly, you will get S1 of t AC cos 2 pi into F1t. So this suffix 1 is correspond to bit value 1. Okay, when you are having bit value 1, whatever the frequency you are getting, that is F1. Similarly, so up to here I have considered like S1, S2. Okay, similarly here also you can represent S2 only. Okay, S2. But here AC cos 2 pi, if you want you can consider F2 or otherwise F0, your wish. Okay, right. So here F1 is the frequency correspond to bit value 1. Just for your reference, this frequency you are getting because of bit value 1, this frequency you are getting because of bit value 0, because of bit value 0. Okay, next one. Bandwidth. Okay, bandwidth of ASK and PSK. Bandwidth of ASK and PSK both are same, that is equal to 2 times RB. 2 times RB. Same. 2 times RB. Whereas here you are getting that entire spectrum is shifting to some other frequency range, right? So that is the reason. So here we will consider F1 is higher when compared to F2. So you can consider F1 minus F2, but if you want modulus, you can consider, no problem. Okay. In addition to that, whatever you got earlier, same thing. 2 times RB. 2 times RB. F1 minus F2 difference, and in addition to that, you are having 2 times RB. Okay. Next one. Next one, probability of error. Probability of error P. Probability of error P. So here in ASK you will get Q function square root of EB by 2N naught, square root of EB by 2N naught. Okay. In PSK you will get Q of square root of 2 times EB by N naught, 2 times EB by N naught, whereas here Q of square root of EB by N naught, EB by N naught. Okay, so just observe here regarding probability of error, Q of root EB by 2N naught, root 2 times EB by N naught, and then EB by N naught. Okay. So here we have used Q function. Regarding Q function, okay, suppose what is the here inside value you are having, that you can consider like x. Okay. If you are increasing x value, then Q of x value will decrease. Okay. As x increases, Q of x will decrease. That means probability of error is going to decrease. Okay. So now just observe. See in the analog communication system, earlier with respect to first chapter modulation techniques, we have discussed among AM, DSBSC, SSBSC, SSBSC is the best. Okay, but when you compare analog amplitude modulation techniques and angle modulation technique together, if you are comparing, from there FM is the best. FM is the best. Now with respect to digital communication, just like there we are having amplitude shift keying, frequency shift keying and phase shift keying. Now let us see among these three which one is the best. Okay, so just observe here. First let us see, whenever you want to compare, okay, you can compare. Earlier also if you want, you can observe with respect to power we have compared, with respect to bandwidth we have compared. Similarly here also when you are representing the binary data in terms of zeros and ones, okay, so in the course of time what will happen, the 0 can become 1 or 1 can become 0 because of the noise. Okay, so here we are calculating probability of error concept. Okay, we are not calculating regarding the power, because here in all the modulation technique you will get same energy, same power, because ultimately you can observe for every bit interval you are representing. Suppose example, you can observe when you are considering positive voltage or negative voltage magnitude wise, because when you perform power obviously you will take peak value square, okay, divide by 2. Suppose if you are considering cos signal or sin signal. Otherwise if you are having constant, that constant square, and then if you are multiplying with bit interval, from there you are getting energy of the signal. So here for all the modulation techniques energy will be same. That's why we are not comparing with respect to energy, because every bit interval we are keeping, okay, every bit we are keeping same interval. That is the reason energy is not going to change. Once energy is not going to change, obviously power also won't going to change, right? So now in this particular digital communication we are comparing with respect to bandwidth and then with respect to probability of error. Okay, so with respect to bandwidth when you observe, here 2 times RB, here 2 times RB, but here 2 times RB plus F1 minus F2. Okay, generally you will be having, suppose F1 is 5 MHz, F2 is 3 MHz, so 5 minus 3 is 2 MHz. Generally this RB you will be having in the order of kilo. Okay, so that means here among all the bandwidths, okay, when you compare with respect to IISc, PSK, FSK, FSK is having more bandwidth. FSK is having more bandwidth. That is the reason with respect to bandwidth that is not recommended. Okay, IISc, PSK is fine because both are having same bandwidth. Now let us observe with respect to probability of error. Okay, so regarding probability of error, so just make a note, as x increases, q of x decreases. As x increases, q of x decreases. What is the q function you are having? Okay, so that q value is going to decrease. For easy understanding, in all the terms under root you are having, right, EV by N naught is same. Okay, so now you can observe here EV by N naught multiplied with what? 1 by 2. That means here 0.5 times. Okay, so in IISc you are getting like 0.5 times x. Okay, EV by N naught whatever you are having I have considered like x. Okay, next here 2 times EV by N naught, that means 2x. So okay, just for easy understanding, yeah, PSK I will write here 2x. Next last one EV by N naught, that is nothing but x. Okay, FSK you are having x. Now just observe, you are having 0.5x, then x, then 2x. Okay, so as x increases, q of x decreases. That means among all 0.5, 1, 2, this 2x is larger. The moment if x is larger, q of x will be decreases, or you can say q of x you are getting minimum in PSK. If you are getting q of x minimum, obviously the probability of error, okay, probability of getting error is minimum in PSK, right? So that is the reason. Now you can observe with respect to bandwidth, IISc, PSK both are same. With respect to probability of error, okay, in fact you can observe probability of error you are getting minimum here. Okay, probability of error you are getting minimum in PSK, whereas 0.5, 2 and 1, 0.5 is what? Minimum. So that means you are getting probability of error maximum. Now you observe, if you are getting more probability of error, definitely we won't recommend that modulation technique, right? So that is the reason here in the digital communication system, among these three modulations, okay, now PSK is the best. PSK is the best because the probability of error is minimum and the bandwidth also required is minimum. Okay, so this is a conclusion point. This is very, very important. So among all the modulation techniques, PSK is the best. PSK is the best. So with respect to analog communication system, I have discussed FM is the best. With respect to digital communication system, PSK is the best. Right? Yeah. So in this particular chapter, whatever we have discussed regarding ASK, PSK, FSK, all this signaling, if you want, you can consider like we have used two symbols, right? We have represented two symbols with the help of one bit. Okay, 0 we have represented one symbol, 1 we have represented another symbol. That means all these modulation techniques, whatever we have discussed, all those are binary signaling, right? So, but you can represent with the help of more than one symbol you can represent. So accordingly you will be having M-array signaling. Okay, M-array signaling. So here regarding M-array signaling, here M equal to 2 power n, where M is the number of symbols, and capital N is the number of bits that you are representing for every symbol, Say for example, n value 1 if you are considering, that means you are using 1 bit. Okay, so that time you are getting two symbols. Okay, similarly n value 2 if you are considering, that time you are getting m value 4. That means when you are having 4 symbols, you can represent each and every symbol with the help of 2 bits. Similarly, if you are having n value 3, you can represent 8 symbols like that. Okay, so whatever the modulation techniques we have seen, like ASK, PSK, FSK, all are having m value 2. Okay, the other name is binary ASK, binary PSK, binary FSK, like that. Okay, similarly, if you are having m value 4, since we have mentioned among all PSK is the best, so accordingly I am representing like 4 PSK. So that means since I have mentioned 4 PSK, that means you are having 4 phase angles, we can say. So accordingly you can consider as QPSK, quadrature phase shift king. Similarly, with respect to 8, if you want, you can consider like 8 PSK, like that, even 16 PSK, etc. Any modulation technique you can consider, okay, etc. with respect to various symbols. Okay, that means you are getting, suppose if you are having 8 symbols, we have to represent each and every symbol with the help of 3 bits, like that. So here regarding the bandwidth, okay, so whenever in the question they will specify regarding raised cosine pulse or spectrum, regarding raised cosine spectrum, they will give the roll-off factor. Alpha is the roll-off factor. Okay, in the question they will specify this value. Okay, generally sometimes they will represent in terms of percentage. That value you can convert into normal. Okay, suppose if they have mentioned like 15%, that is nothing but 0.15. Okay, so that time even for M-array signaling or even this concept, okay, so regarding that, whenever you want to calculate bandwidth, the formula is RB into 1 plus alpha divided by log m base 2. See here with respect to M-array signaling, this 1 plus alpha won't come. Okay, 1 plus alpha won't come, but you will be having RB by log m base 2. But with respect to whenever they specify raised cosine spectrum, that time alpha value they will specify, that you can consider. Suppose if they have mentioned in the question that alpha value is like 100%. 100% means its value is 1, right? 100% means its value is 1. So alpha value you can consider like 1. Okay, so sometimes if they have given like 0.15, you convert into percentage. That percentage value you have to consider. Okay, here suppose for easy understanding I am considering alpha. If they have given like 100%, that means alpha value is 1. 1 plus 1 is what? 2. 1 plus 1 is 2. Then suppose if you are considering m value 2. Okay, so 2 log 2 base 2 is what? 1. So you are getting numerator is 2 into RB. You can observe. whatever formulas earlier you got with respect to PSK or ASK, you are getting same answer, right? So in that way you can correlate. Okay. Suppose if they have mentioned 15%, then you will consider 0.15. So accordingly you are getting different formula. And even if they mention different symbols, then accordingly you can consider M value accordingly. Okay. So with this we have completed 6th chapter, right? So for instrumentation branch, as I mentioned earlier, the first 2 chapters and then 5th and 6th chapters are part of the GATE syllabus for communication system subject. Okay, now I am going to discuss the last chapter, that is, so whatever all the chapters are there regarding communication system subject, all these chapters are part of the syllabus for EC branch. Okay, now we are going to see regarding the last chapter, that is information theory. So chapter 7, information theory. So regarding information theory, okay, what are the important points and formulas are there that I am going to cover now. Okay, so I hope all of you know the basic formula. The relation between information and probability of occurrence of that event are inversely proportional. So I is proportional to 1 by P. Okay, so in order to remove this proportionality constant, we will use logarithm symbol. Okay, logarithm symbol, base value 2. I equal to log 1 by probability base 2. Okay, so here information you will get in the order of bits, or in the units you will be having bits. Okay, suppose if probability equal to 1, probability of occurrence is 1, that time log 1 by 1 is nothing but log 1 base 2 is 0. So information is 0. Suppose if probability is 0, that time you are getting 1 by 0 is infinity, that means very high value you are getting. Okay, information is very high. Information is very high. Next, so this is regarding information basic formula, log 1 by P base 2, log 1 by P base 2. Now the next one is entropy. Next one is entropy. Entropy is nothing but the average amount of information. Average amount of information. Average amount of information. Okay, so entropy we can represent with the letter H, so which is equal to summation over I equal to 1 to n probability of, okay, I am representing in short P suffix I into log 1 by Pi base 2. See here, for every event or for every symbol, whatever the probability of occurrence is there, that we are considering, and then information, right? So we are multiplying those two like that for all the combinations we are considering. From there, on an average, you are getting how much information you are representing or how many bits you are representing, right? So here units will be how many bits you are representing for every symbol on an average. On an average, for every symbol, how many bits you are representing. Okay, so summation over I equal to 1 to n probability into log 1 by probability base 2. This is the entropy formula. Okay, next one is information rate. Information rate, okay, in some question they will mention like this, information rate, or in some question they will mention like data rate. Okay, all are same only. Information rate or data rate, or in some question they will specify bit rate. So in some question they will ask information rate or data rate or bit rate, all are same. Information rate or data rate or bit rate, all are same. All are same, right? So here regarding this one, what you have to do, whatever the entropy you got, okay, entropy units are what? Bits per symbol. Okay, just you can apply. So when you're having lot of formulas, okay, sometime you may forget even during the GATE exam, no problem at all. Just recall the basic. Once if you are recalling the basic, from there you can easily answer. Here bit rate means what? How many bits you are transmitting in second, right? So that means units are what? Bits per second. Units you are getting bits per second. Yes or no? Bits per second. Now just observe. Just now we have discussed regarding entropy. Units you are getting bits per symbol. Bits per symbol. So here I will consider entropy. Entropy. So that entropy units you are getting bits per symbol. Entropy units you are getting bits per symbol, right? Now here I want what? Bits per second. Bits I already having in the numerator. Okay. Denominator I require second. Okay. I'm writing here. Denominator I require second. But now here denominator symbol is there. In order to get cancel, here numerator I have to consider symbol. Okay. So now I have to consider one more term in such a way that that particular term is producing how many symbols in 1 second, right? So regarding that you can represent like symbol rate. Okay, symbol rate. Whatever the information source you are using, with the help of that information source, how many symbols on an average you are producing in 1 second, from there you are getting symbol rate, and that symbol rate multiply with entropy, and from these two, here symbol will get cancelled, you are getting bits per second. So that is nothing but bit rate or data rate or information rate. See, when you are having single bit, we will call it as bit rate, suppose example. But when you are having group of bits, okay, group of bits, if you want you can call it as data, okay, or information, all are same only, okay. See, ultimately you are getting what? In 1 second, how many bits you are transmitting, that is nothing but bit rate, okay. Okay, so this is about regarding the entropy and regarding the information rate. Okay, now let us proceed further. So in sometimes in the GATE exam regarding this particular chapter, okay, you regarding entropy you will be having various, okay, just like in the probability concept when you have studied from the mathematics subject, okay, you might have studied joint probability or conditional probability, etc. So similarly here, accordingly you will get the corresponding entropies, okay. That time don't get any confusion or don't get panic, just recall the basic formula of entropy, and from there you can just represent the other probabilities, that's all, other representation for the corresponding entropies, that's all. So next one, that is here h of x comma y, so this is like joint entropy, okay. Earlier also we have used, when you are having two variables, that time we have used joint probability distribution function or joint probability density function, like that, right? So here joint probability, okay, here h is their entropy, right? If I used p, that is the probability, okay, joint entropy. So since you are having two variables, okay, when you are having with respect to one variable, that time you are having one range or one sigma, so accordingly for two variables you will be having two sigma, okay. Summation over I equal to 1 to m, summation over j equal to 1 to n, Since you are having two variables, accordingly I have to consider joint probability. So probability of xi comma yj, probability of xi yj, okay. See, now you can just recall this formula, probability into log 1 by probability, but in this case in place of probability, joint probability, and same thing you can consider log 1 by joint probability, base 2, okay. Similarly, so this is your joint entropy, okay. Next one is conditional entropy, conditional entropy. Okay, so regarding that, so here h of y given x, so here x equal to xi, okay, it is just like a given b, right? So in the similar way you can observe here you are having conditional entropy y given x. Okay, now since I have considered here xi, that means I have to consider the range with respect to I. Okay, you have to consider the range with respect to I. Sorry, here x equal to xi, this is fixed already. P of a given b, that means here this is already fixed. That means y value is varying. So regarding y values, we are having j equal to 1 to n, right? So that one we have to consider. So here summation over j equal to 1 to n. Here x value we have fixed. That is the reason we have to consider y values. So regarding y, you are having j equal to 1 to n, probability of. Okay, regarding y you can consider yj given x equal to xi. Okay, x equal to xi. So this is the probability. Now consider log 1 by probability. Yj given x equal to xi, base 2. Okay, probability into log 1 by probability. Okay, see here joint probability, according to joint entropy. Here conditional probability, according to conditional entropy. If you are having normal probability, then accordingly normal entropy. That's all. Okay, next, entropy of input. That is h of x. Entropy of input, that is h of x. So that you will get I equal to 1 to m probability of xi into log 1 by probability of xi base 2. Okay, similarly entropy of output, that is h of y. So with respect to y, we are having the limits j equal to 1 to n, probability of yj into log 1 by probability of yj base 2. 1 by probability of yj base 2. Just like earlier, you can observe probability into log 1 by probability. But in general, when you are having in the information theory, okay, so when you are representing the channels, okay, so you will be having source, you will be having the destination. In between you are having the channel. So regarding the channel, okay, at the input side we used to represent x symbols, at the output side we used to consider like y. Okay, so output you are receiving because of transmitted so and so symbol x, right? That is the reason we are considering y given x. Okay, that is accordingly you are getting the conditional probability. So this is with respect to input entropy, this is with respect to output entropy. Okay, so here whether you have to consider I values or j values, no need to worry too much. Okay, with respect to y you are considering the range, with respect to x you are considering the range, that's all. Okay, yeah. Now if x and y are independent, if x and y are independent, then h of x comma y, is equal to h of x plus h of y. Okay, if these two are independent, just like P of A union B equal to P of A plus P of B, like that you can correlate. Okay, next, so in this case, since these two are independent, there is no intersection part regarding the entropies of x and y. So that is the reason here the mutual information I of x comma y is equal to 0. Okay, so in this case in this case h of y given x is same as h of y. Similarly, h of x given y is same as h of x. Because these two are independent, whatever this condition probability is same as h of y, it is not depending on other like that. Okay. Now let us see if x and y are dependent. If x and y are dependent, if x and y are dependent, then in that case you have to write h of x comma y. H of x comma y is equal to h of x comma y is equal to h of x plus h of y given x. H of x plus h of y given x. Similarly, you will be having one more formula, that is h of y h of x given y. H of x given y. Okay, h of x comma y equal to h of x plus h of y given x. Okay, h of x comma y equal to h of y plus h of x given y. How to remember this one? Just you can correlate like this. Here x is in the denominator. Okay, here y is in the denominator. Like that you can correlate. Next, regarding the mutual information I of x comma y. Regarding the mutual information I of x comma y, that is nothing but h of x minus, see from this we are subtracting this one. Okay, h of x minus h of x given y. Similarly, you will get the similar formula or equation or value if you are subtracting. Okay, if you are considering h of y, okay, from here you can subtract this one. From here you can subtract this one. H of y minus h of y given x. See, for easy understanding, you can correlate. Suppose if you are able to remember these formulas, from here you can easily correlate here. See, here x and y are independent. Okay, x and y are independent. That time h of y given x is same as h of y. So h of y plus h of x. Yes, this relation you are getting. Similarly, h of x given y is same as h of x. Yes, h of x plus h of y, same thing you are getting. Right. Next, here h of x given y is same as h of x. Then h of x minus h of x, 0. Similarly, here h of y given x is same as h of y minus h of y, you are getting 0. Okay, so try to remember this one. It is very simple. Okay, just remember either this one or this one. With the help of any one set you can write other. Okay, regarding this I already given the hint, h of x plus h of y given x. Okay, h of y plus this y should be there in the denominator, that's all. Okay, now once if you are able to write this one is very simple. H of x when you are considering. Okay, now consider other term. Okay, this term you have to subtract. Similarly, when you are considering this one, other term you have to subtract. That's all. Once if you are able to write these equations, from here you can easily write these equations, because this is a special case of that one, right? Okay, now in general, whatever the information or mutual information you are getting regarding that, okay, in general you can write the condition. It will be starting value will be minimum. That minimum value is 0 because it is information, right? It is 0. We already discussed when the probability of occurrence is 1, because regarding the probability the minimum value is 0, maximum value is 1, right? When you are considering maximum probability, that time you are getting information as 0. Okay, when you are considering minimum probability, that time you are getting maximum information, right? So here the information or mutual information exists in the interval 0 less than or equal to I of x comma y less than or equal to minimum of h of x comma h of y. Minimum of h of x comma h of y. So among these two, whichever is the minimum, that will be the upper limit. Okay. So next one, Shannon-Hartley law. Okay, we can use this particular law for calculating the channel capacity. So this is one of the important formula. So channel capacity equal to B into log 1 plus S by N. Log 1 plus S by N. So here B is nothing but bandwidth. And here S by N is nothing but signal to noise ratio. Here you are having channel capacity. So here channel capacity, you will get the units in the order of bits per second. See, the reason is very simple. Earlier we have calculated what? Bit rate. That means how many bits you are transmitting in 1 second. So those bits where you are transmitting in the channel only. So ultimately the channel capacity, earlier also we have told, say for example when you are discussing with respect to analog communication system, that time I have used the word bandwidth. Okay, here since we are discussing in terms of digital, that is the reason the same bandwidth only here in terms of other terms we are calling, that is capacity. Okay, so among the signal bandwidth and channel bandwidth, the channel bandwidth should be maximum, or we can say it is a more, then only you can transmit multiple signals. In the similar way, for any modulation technique, regarding digital modulation technique, whenever you are transmitting the bits, okay, so in 1 second how many bits you are able to transmit. Okay, so from there you are getting the bit rate with respect to that modulation technique. Now like that, how many signals you can transmit in the given channel, so from there you are getting the capacity of that particular channel, right? So that means here also units will be with respect to bit rate, so that is nothing but bits per second. Suppose for the timing, if you have ignored bits, okay, suppose when you are dealing about analog communication system, that time we never use the term bit, right? So just ignore bit, then per second, whenever you are having per second, that is nothing but the units correspond to frequency. So the frequency units are what? Hertz. So accordingly you are getting the channel bandwidth or signal bandwidth. So earlier we have used the term bandwidth. Here in this chapter we are using the word channel capacity. Both are same. Okay, you can correlate like that. Okay, so next one. So this formula you can use, and here one more important thing, here whatever S by N is there, that value is the normal value. But suppose in the question if they have given in the order of decibels, that decibel value you have to equate to 10 log S by N. From there you can find normal S by N. After that you can substitute here. Okay, that is the most important. Next, channel capacity. So here in this chapter we will be having various channels. Okay, for the timing I am considering 2 special channels. Okay, so for that I am writing the corresponding channel capacity. So for binary symmetric channel, the channel capacity is 1 plus probability into log p base 2 plus 1 minus p probability into log 1 minus p base 2. Okay, 1 plus probability into log p base 2 plus 1 minus p into log 1 minus p base 2. Okay, similarly for we are having one more channel, that is called binary eraser channel. For binary eraser channel, the channel capacity is 1 minus p. Okay, as for exam point of view, you can remember for binary symmetric channel, the channel capacity, and binary eraser channel, the channel capacity. Okay, so here whatever you are getting, suppose if you are considering minus as common, so this formula you will get for entropy, right? So for easy understanding, this formula how to remember is 1 minus entropy. 1 minus entropy you can remember, whereas for binary eraser channel 1 minus p. It is simple formula. Okay. So next one is Hamming code. So here one important relation will be there, like minimum distance. Okay, when you are having 2 successive Hamming codes, how many bits are getting differed? Right. So that minimum distance is nothing but d min. Here one important relation will be there. Okay. So d min is less than or equal to n minus k plus 1. n minus k plus 1. So here n is nothing but the number of bits of that particular code word. N is nothing but number of bits of code word, okay, and k is the information bits, okay, and k is the information bits or message bits. K is the information bits. Now n minus k is nothing but the number of parity bits. That we are using. Okay. So here m value is an integer. So for all the m values which are greater than or equal to 3, okay, you can write down the relations regarding the number of bits of the code word, which is nothing but 2 power m minus 1. 2 power m minus 1. Just like when you're having 3 bits, you will get 2 power 3 minus 1. Total 8 minus 1. In general, you will get 8 combination, but here we are using 8 minus 1 like that. Next, k equal to k is what? Information bits. K is the information bits. And here, okay, before writing that one, I will consider parity bits. N minus k equal to m. Right. So n equal to this one, n minus k equal to this one. So from here n equal to what? M plus k. Right. So or from here I can write k equal to n minus m. So n value I am writing 2 power m minus 1, and that minus m I am writing here. Okay. Okay, for easy understanding, you can substitute m value 3. Accordingly, you are getting 8 minus 1, that is 7. Okay, and from here you can get k value, and from there you can find out parity bits. Okay, in general for 7, 4 Hamming code will be there. So there you are using 4 message bits and 3 parity bits. Okay. So regarding parity bits, when you have considered 3 bits, you will write 8 combinations. So wherever you are getting 1, the respective bits you have to observe, and among that you have to perform the XOR operation. From there you will get regarding parity checking bit like C1, C2, C4. Okay. So from there, if you are getting whatever the bit value you are getting, so from there you can identify whether any bit error is there or not. If error is there in that particular bit position, you are coming to know, okay, with the help of the parity bits. Okay, with the help of parity bits, you are coming to know in which particular bit you are having the error, and you can, with the help of that particular bit, okay, you can make, suppose if you are getting 1, you can make it 0. If you are getting 0, you can make it 1, because in that particular bit there is the error. Okay. So with the help of Hamming code, we can check only 1 bit error, right? So the moment you are getting 1 bit error, so we can correct it. Suppose if there is no error, you will get 000 like that. Okay. So with this, we have completed all the chapters regarding communication system subject. So in the previous session and today in this session together, in these 2 sessions, we have discussed all the important points and formulas regarding the overall subject communication. So as I mentioned earlier, all these 7 chapters are the part of the syllabus for EC branch, whereas for instrumentation branch, the first 2 chapters and then 5th and 6th, only 4 chapters are there as the part of the GATE syllabus for EC instrumentation branch regarding communication system subject. Okay, so I hope all of you got great learning in the less time regarding the communication system subject, because we are having lot of formulas and equations in this particular subject, because this syllabus of this particular subject is very vast, right? So you will be having lot of formulas. So I hope all of you got the how to remember what are the important points are there. See, if you want to remember, if you want to by heart the equation, then you may forget. Okay. Okay, if you want to remember the equation, if you are doing the by heart, then you may, most of the times you will forget. But if you are remembering the formulas with the help of one approach, okay, while solving the question, or with the help of whatever the concept is there, with the help of that, if you are remembering, then definitely you can remember the formulas for longer, right? So I hope all of you can easily remember whatever the concepts, whatever the formulas we have discussed in these 2 sessions regarding communication system subject. So wish you all the very best for your coming GATE exam. Thank you everyone.